Hi, this is a video for Calculus BC section 9.7. This is about Taylor polynomials and approximations, as well as Maclaurin polynomials. We'll see the similarities there here in a little bit. But we're going to start off with a calculator exercise. In this calculator exercise, what I want to do, this is going to be kind of the opposite side of what we did at the very start of chapter 9. Instead of starting off with a mystery function, we're going to start off with a known function. We're going to try to fit a polynomial to it. So in other words, if I've got cosine of x, there's the graph of cosine of x. I'm going to try to construct a polynomial that approximates cosine of x. In order to do this, we have to pick a point that we want to center on or center at. We could pick, 1 or 2, 3, -2, whatever. Any of those would work, but a very common one is to try to center our polynomial at 0. And so what I'm going to do is I'm going to look at my graph of cosine of x, and I'm going to ask myself what is the value of the function when x is 0. And of course, if you remember cosine, when x is 0, y is 1. So I'm going to go to my y equals, and I'm going to make my approximating polynomial my y2. So I'm going to start off with y equals 1, and I'm going to graph that. And of course, you can see that when I graph that, right there around x equals 0, this is a really good approximation, but once you move away from 0, it's a really terrible approximation. So we want to try to match some other stuff in here. So some other things we could match is we could try to match the slope of cosine with our polynomial. So the slope of cosine, of course, is negative sine, and the value of negative sine at 0 is just 0. So if you remember with the polynomial that we constructed at the start of chapter 9, the degrees kept on building. You look at your y equals here, we started off with 1, of course that's 1x to the 0. So you'd expect that our next term would be an x, the term after that would be an x squared, maybe an x cubed, x to the 4th, x to the 5th, so on and so forth. We'll find out a little bit that first derivative matches up with x, and so we found out that the value of the first derivative at 0 was 0. So if you wanted to, you could put plus 0x. Of course, that's not really going to change anything. Of course, we look at the graph, and it's like, well, it's the same thing. So that didn't really help. One other thing we could try to match would be the concavity. So we can see that around 0, cosine is concave down, and concavity goes with the second derivative. So the second derivative of cosine is negative cosine, and when x is 0, negative cosine is negative 1. So I could go back to my y equals, and I could add a term on here. So it would be minus x squared. We can see that those powers are progressing from 0 to 1 to 2. So now let's look at the graph. So of course there's our cosine, and now you can start to see that our approximating polynomial is much better. Okay, interesting result. Obviously it's not perfect. Can you see how the red graph here, our approximating polynomial, is a little bit too skinny, right? So if you remember from the start of chapter 9, we tried to make it fit as best we could. And you can experiment with this. But the bottom line is we need the x squared to, that term to allow that, what amounts to a little parabola, to be wider. So we need to divide by some number. And you might experiment. You might divide by 8. You look at that. I think you'd see that if you divided by 8, we went a little bit too wide, right? Yep, too wide for sure. We went from too skinny to too wide. And so, you experiment a little bit more, and, eventually you'd get pretty close. The truth is the exact value that goes there is divided by 2. And so you graph these two together, and you should be able to see here in a second that, that dividing by 2 really did help, and it made our approximating polynomial just about the right width. Well, we can keep going here. We're gonna try to make this better, and so if we tried to keep matching derivatives here, our third derivative f triple prime of cosine is just sine. Just notice that every time we get sine, the sine of 0 is 0, and so if I go back to my polynomial here, our x cubed term is just going to be 0x cubed. And that's because on every odd powered term, we end up with sine of 0, which is 0. So you put 0x cubed if you want to just kind of notice the pattern a little bit, but of course you don't have to put that. Well, finally we get to the fourth derivative. So the fourth derivative is cosine. Fourth derivative of cosine is cosine. And of course cosine is 0 is 1. So I'm going to put plus 1 x to the fourth, right, as we're moving our powers up. And I'm going to try to graph that. So, you take a look at this and you can see that we've got this nice quartic. But like before, it seems like it's not wide enough, right? It seems almost like we, have a pretty good match there, but if we could widen this out, it could be a lot better. So, you try all kinds of things here as far as, what we need to divide x to the fourth by. You could try a 10, you could try a 20, a 2 again, whatever. But you're going to find that eventually the appropriate number is 24, which happens to be 4 factorial. So let's take a look here at what that looks like if we graph our cosine graph, and then here's our approximating polynomial coming in there. And you can see we got a pretty good looking approximation, right? It really seems to coincide for quite a while. Of course, the pattern here, maybe you're starting to see it. If I go back to my y equals, you can see that every odd powered term is 0, and every even powered term is not 0. And so I'm going to add one more term to fit this pattern. So if my previous term was plus x to the fourth over 24, probably the last term we'll do here would be minus x to the sixth over 6 factorial is the appropriate division there on that last term. So we end up with something like that. So let's take a look at one more comparison of the cosine graph with our approximating polynomial. And we can see that we have made it even a little bit better. Not bad, not bad. So did you notice that obviously every single term we added, as long as we divided by the appropriate number, we really widened out the interval of convergence where our polynomial approximation approximated our cosine graph. So there's a number of implications here, but for the moment, all we're going to do is we're going to practice making these polynomial approximations. So that's what this is all about right here. So a man named Brooke Taylor is credited with developing this with his Taylor polynomials, Taylor's theorem. And so here it is. This is how we construct these. And this will work for any of the functions that we deal with. So here we go. The nth Taylor polynomial centered at C, and so C, of course, could be any number, is equal to the following. So P sub n of x, this would be the polynomial approximation, equals f of c, that's just the value of the function that we're trying to approximate at our centering value, plus f prime of c, so we're trying to match the slope there, times x minus c. And then you start to see the pattern develop. The third term right here, f double prime of c over 2 factorial, x minus c squared. You can see how everything is kind of progressing up in degree and in derivative. Third derivative of c over 3 factorial times x minus c cubed. That's our fourth term. And then you see this nice general term, this nth term out here on the end. So that's the formula. You can look at that as something you need to memorize, or you can look at the pattern and try and get the pattern down. But we'll practice it quite a bit. I think you'll have a great chance of having that just essentially memorized by use. And then the other type of polynomial approximation we'll look at is called a Maclaurin polynomial. And a Maclaurin polynomial is a Taylor polynomial, but it's specifically centered at 0. And so if you see Maclaurin polynomial, that is just another way of saying a Taylor polynomial centered at 0. The Taylor polynomial can be centered anywhere, 0, 1, 2, 5, 10, negative 30, negative 3, whatever it is. Maclaurin polynomial is specifically referring to a polynomial approximation centered at 0. Hopefully you can see that the terms progress in the same way. F of 0 matches up with f of c. F prime of 0 times x matches up with this term up here, so on and so forth. It really is the same thing. One little note off to the side here is f with the parentheses n up there kind of in an exponent does not stand for f to the nth power. It stands for the nth derivative. So if you see something like this, that just means the fifth derivative. Okay, so I thought we would do an example. It might seem a little on the silly side, but it's really not. What we're going to do is we're going to try to approximate a polynomial with a polynomial. So like I said, that might seem kind of silly, but it really isn't. I just want to prove to you that this works. So we kind of know in the end what we should end up with, right? We should end up with the same polynomial. But I just want to prove to you that this works. So we're going to do a Maclaurin polynomial, which means centered at 0. And here we go. So the first term, I'll put P of x for polynomial approximation is equal to, the first term is f of 0. So f of 0, that's our function over here, is equal to 0 plus 0 plus 0 plus 7. So there's our first term. You might say, oh great, okay, so I see we matched that 7. Whoops, there we go. I see we matched the 7, big deal. Let's keep going. The second term is f prime of 0. So I'm going to write over here f prime of x. So f prime of x is equal to 8x to the third minus 9x squared plus 5. So f prime of 0 is equal to 5. So we come over here. Our next term is going to be f prime of 0 times x. So 5x. Hope you can see that this is building up to exactly what we were expecting it to be. Okay, then the next term would be f double prime of x. F double prime of x is 24x squared minus 18x. And I'm imagining you can see that f double prime of 0 is actually 0. So our next term would be plus 0x squared over 2 factorial, also known as 0. Okay, so it's matching up, right? Let's keep going. Our third derivative is going to be f triple prime equals 48x minus 18. And f triple prime of 0 is equal to negative 18. And you might think, haha, this is finally where it didn't work out. But it actually does. We're going to write minus 18 x cubed over 3 factorial. It's actually going to work out pretty good. And then finally, f quadruple prime, and this is probably where I would write f with a little 4, so fourth derivative of x is equal to 48. So of course the fourth derivative of 0 is also 48. And we come back over here and we write plus 48 x to the fourth over 4 factorial. Well, I think you're going to see that this works out great because my polynomial approximation for my polynomial would be 7 plus 5x. That third term is just 0, so I'm not going to write that. 3 factorial is really 6, and 18 over 6 is 3, so minus 3x cubed. 4 factorial is 24, and 48 over 24 is 2, so 2x to the fourth. So it's exactly what we would expect. Shouldn't a polynomial approximation for a polynomial be that polynomial, right? And so that's going to be the only time we ever do that. I just want to prove to you that this actually works. And we're going to use this, of course, on some other things. So the next one here is going to be number 2, and that's the one we just developed. So we're going to just go ahead and use Taylor's theorem or Taylor's formula to develop out the polynomial approximation for cosine of x. So here we go. It says 6th degree. So 6th degree, of course, means we're going to have x to the 6th is our highest power. So here we go. The first thing we're going to write here is p of x equals, and our first term is going to be f of 0. So I'll just write these over here. So f of 0 is equal to cosine of 0, which is 1. So again, just using the Taylor and the Maclaurin construct for these polynomials. So our first term is 1. So our next term comes from f prime of 0. So f prime of x is equal to negative sine of x. And of course, f prime of 0 then equals 0. So that would be plus 0x. All right, so then our second derivative, well, we're going to the 6th degree here. Second derivative is equal to negative cosine of x. So the second derivative at 0 is equal to negative 1. So I'm up to the third term, so it's going to be minus 1x squared over 2 factorial. All right, moving on. Third derivative of x is equal to sine of x. And third derivative at 0 is equal to 0. So once again, that odd degreed term ends up being a 0. All right, let's keep going. Fourth derivative of x is equal to cosine of x. So the fourth derivative of 0 is equal to cosine of 0, which is 1. So that would be plus 1x to the 4th over 4 factorial. Let's see here. Let's go fifth derivative. So the fifth derivative is equal to negative sine of x. And if it's okay with you, I'm just going to recognize that, fifth derivative of 0 is 0. So I'm not going to write this term over there. I'm just going to move on to my final derivative here, the sixth derivative. And that would equal negative cosine of x. So the sixth derivative of 0 is equal to negative 1. So that would be minus x to the 6th over 6 factorial. And so that right there is an approximation for cosine using 6th degree Maclaurin polynomial. This question does ask us to take it a step further and use that polynomial to approximate cosine of 0.1. So that would be p of 0 equals, not p of 0, p of 0.1. P of 0.1 equals, and so now we just, would maybe turn to the calculator here. Obviously 0.1 to the, I don't know if it's that bad, but I think the calculator would be handy to do here. So take a minute, calculate this out, and we'll check our answer. Okay, so with my polynomial approximation going out there to the 6th degree, I get this, 0.995004163. So I would encourage you to then use your calculators to calculate, actually cosine of 0.1. And I think you'll find that it's extremely close. Let's talk about why that is. For one, we are very close to our centering point, right? Our centering point was 0, and we just calculated 0.1 as an input for both the polynomial and the cosine. So at only 0.1 away from our centering point, we should be quite close. And you can tell when you compare, we are very, very close. Okay, let's move on to another here. Let's work on constructing these. So number 3, a little bit different. It says, find the 4th degree Taylor polynomial for f of x equals ln of x, and now we're centered at c equals 1. So this is different. The previous one we did, we were centered at c equals 0. That made it a Maclaurin polynomial. This one, we're centered at something other than 0, making it truly a Taylor polynomial. So again, as always, I'd encourage you guys to pause the video here. You've got the notes in front of you. You got the basic Taylor and Maclaurin construct. I encourage you to try it. Pause the video, put the video back on, see if we agree, and hopefully that'll give you some confidence moving forward. All right, so we're going to use our basic Taylor construct. You refer back to it previously in your, the above part in your notes. Now here we go. I'm going to represent our polynomial with I'll use the letter P again. You could use maybe a T for Taylor, but P of x is equal to. So the first term is going to be f of our centering point. So f of 1. So I'll make some little notes off to the side here. F of 1 is equal to ln of 1, which of course is 0. Okay, so our first term is 0. Not off to a promising start, but we're just going for the 4th degree. Let's see what else we can come up with. So my first derivative is f prime of x, and that's equal to 1 over x. And so f prime of 1 is just 1. So it's going to be plus 1x. Our second derivative is going to be negative x to the negative 2. Let me fix that. Okay, so that of course means that f double prime of 1 is equal to negative 1. So that would be minus x squared over 2 factorial. All right, moving on. Third derivative time. Third derivative is equal to 2x to the negative 3. So that means that the third derivative at our centering point of 1 is going to be 2. So we are at 2x to the third over 3 factorial. You can tell if we're going for 4th degree, we only have one more to go here. So 4th derivative is equal to negative 6 x to the negative 4th. So the 4th derivative at 1 equals negative 6. So we end up with minus 6x to the 4th over 4 factorial. Okay, we can do a little simplifying here. Let's do that. So p of x is equal to x minus x squared. Well, 2 factorial is just a 2. And then the 3 factorial is, of course, 3 times 2 times 1. So that 2 in there would cancel with the 2 above. And we just end up with x cubed over 3. I think you'll see something similar happen with this next term. Of course, 4 factorial is just 4 times 3 times 2 times 1. So I think the 3 and the 2 would cancel with the 6. So I'd just be left with minus x to the 4th over 4. I think you can start to see a pattern taking shape here. I'm guessing the next term would be plus x to the 5th over 5 plus dot, dot, dot. Keep going. Definitely an alternating series. And it doesn't say this, but we could definitely write an nth term. Let's do that. So the nth term for this would be plus dot, dot, dot plus negative 1 to the, let's see here. If we go negative 1 to the n, we could go, you don't have to be negative n to the n plus 1 if I wanted to go x to the n over n. Yeah, so that would be a good nth term there. You didn't have to do that, but just kind of a aside there. Okay, I hope it's going well for you. I think we've got a couple more examples here. Yeah, I think we'll go ahead and do a second video for those. Yeah, we'll do a second video for those. So probably enough for now. Keep practicing, and you want to see that second video, it'll should be up next.